If you take two identical trays of water, one filled with boiling hot water and the other with water that is already near freezing, and place them both into a freezer at the same time, logic tells you exactly what should happen. The cold water has a massive head start. It is already at the finish line, just waiting to cross over into ice. The hot water, on the other hand, has a mountain to climb. It has to cool all the way down just to catch up to where the cold water started. Common sense dictates that the cold water will freeze first every single time, but the universe has a way of mocking our common sense. Under the right conditions, the boiling water will actually freeze faster than the cold water. It is called Mpemba effect. The effect is named after Ernesto Mpemba, a Tanzanian high school student who in 1963 noticed something strange while making ice cream. He observed that his hot milk mixture froze solid before his classmates' cold mixtures. When he asked his teacher about it, he was ridiculed, but he refused to back down. He eventually convinced a visiting physics professor to test it, and sure enough, the student was right. But how is this physically possible? How does heat act as a shortcut to freezing? There isn't just one answer. It is likely a combination of several chaotic forces working together. First, we have evaporation. When water is hot, it steams. That steam is water molecules leaving the container and taking a massive amount of heat energy with them. This rapid evaporation effectively reduces the total volume of water left in the tray. Since there is less water to freeze, it can happen faster. The cold water doesn't evaporate nearly as much, so it has more mass to cool down. Then, there are convection currents. In a cup of hot water, the temperature difference between the hot liquid and the cold freezer air creates violent movement inside the fluid. The water circulates rapidly, bringing hot water from the center to the edges where it can lose heat quickly. In a cup of cold water, these currents are sluggish or non-existent, meaning the heat is trapped in the center for longer. Finally, there is the bizarre concept of supercooling. You might assume water always freezes at 0 degrees Celsius, but that isn't strictly true. Pure water can sometimes cool well below 0 down to negative degrees without turning into ice, simply because the molecules haven't found a starting point to form a crystal. This is called supercooling. Some research suggests that hot water, because of how it changes dissolved gases or impurities during the heating process, is less likely to supercool. It hits 0 and freezes immediately, while the cold water might not freeze at exactly 0. The Mpemba effect highlights that real-world physics doesn't always follow simple linear intuition. It reveals surprising, complex behaviors hidden in the most ordinary processes. Subscribe if you want to learn more about the physics of your kitchen.